very pleased to be able to present Dr. Jack Treffner to you. This is your first visit to ASARG, so
great to be here, guys.
Virgin, so be gentle with him. But Jack's got a fantastic background in motor control and motor learning. He's worked in some of the best labs around the world and with some of the best people in our field. So I'm not going to take up any more of his time, but I did notice that many of you were eating snacks at lunch, so I think we'll give him an extra 10 minutes in the lunch break to make sure he's got as much time as some of these
I'll have to get you another hat.
PhDs. Okay, so away we go.
Thank you. Yes, first time here, and thank you very much to Sarah Kate for inviting me, and actually to Chris for urging me to come along. Look, I want to give a little bit of a historical overview of some of the work that has happened in the last 20 years within 20 minutes. So it's going to be a real challenge. This is where most of us are at when it comes to starting a skill we are not familiar with. And this is where we want to get to, a much more coordinated situation. Now, beautiful presentation in the last 20 minutes was actually talking about the phasing, the synchronization, the synchrony between the tools, between the objects, between the components or constraints that are part of many sports, whether it's a football or an oar or a tennis racket. There are these appendages, these implements that are imposing constraints upon the body. So now everybody's talking about constraint-based approaches to learning. And I want to give you some refresher on some of the big insights that have come from precise experiments on constraint-based learning. So this is coming from the coordination dynamics perspective, the self-organization perspective, and, as I'm going to show you, the pendulum dynamics, the handheld pendulum dynamics perspective. So I was at the University of Connecticut in the late 80s, early 90s, where I did my PhD. And there we were developing, largely inspired by Michael Turvey, we were developing the handheld pendulum paradigm. So as you all know, the period of a pendulum is related to its length. T is equal to 2 pi root L over G, which is related to the moment of inertia. So we can manipulate the natural frequency and the comfort mode frequency that somebody will swing a pendulum, such as a limb, or an artificial limb, such as a handheld pendulum, all day. So the natural frequency is related to the length. Okay, this is higher frequency, this is lower frequency. Okay, same mass, different moment of inertia, different resistance to rotation. Moment of inertia is resistance to rotation, right? So, yeah, this is a unimanual experiment, but my own work focused on bimanual coordination. So in the old days, you had a sonic digitizer here, which could get the relative phase or the synchrony or lack of it between two limbs. And so this is the old paradigm some of you are familiar with of anti-phase versus in-phase coordination. Okay, so 0 degrees in phase, 0 degrees in phase relative phase, 180 degrees out of phase. Or something in between, such as 90 degrees. And the experiments I'm going to show to you are going to summarize where there's an imposed biomechanical asymmetry. Either a higher frequency in the dominant hand, the right hand, or a higher frequency in the non-dominant hand for a right-hander and for left-handers. So I'm going to compare right-handers, left-handers in some of this data. Okay, see how far we get. Relative phase, briefly, is the measure of synchrony between two time series of amplitude here. Here's, for example, the right hand and left hand. We can say that the right hand is leading the left hand by about 130 degrees. Or similarly, the left lags the right by 230 degrees. This adds up to 360 degrees, right? So relative phase gives you a single number that captures coordination. The big thing in the last 20 years is coordination dynamics. We're now doing the physics of pattern. We're now looking at the relative phase velocity or the relative phase acceleration. So it's Newtonian mechanics, not in terms of position, but in terms of pattern, relations between moving things. So this is the otherwise known as the synergetics perspective, a word developed by a theoretical physicist who invented the theory of the laser, which shows how the laser goes from one state to another, the phase transition concept, which has now been applied to people looking at gait transitions such as walking to running, trotting to galloping, and horses. So they're very precise physical measurements that support the synergetics or the phase transition paradigm. Critical fluctuations just before the transition from 180 degrees to in phase. And of course, 180 degrees might be the more stable pattern, depending on the task, such as walking 180 degrees is more stable than in phase. Right? So it just depends on the context. Don't think that 180 is always the less stable. But in the paradigmatic examples, Scott Kelso, 30 years ago, was looking at fingers, and as the fingers go faster and faster and out of phase, there's a transition to in phase, spontaneous phase transition. Then he went to work with a theoretical physicist in Germany showing that, this corresponds to the mathematics of stability. So physicists like to look at the world in terms of energy landscapes. This is the potential well notion that many of you might have come across, the notion that you've got stable and unstable space, with minimum stability and maximum stability. And as some sort of control parameter such as frequency or rate is increased, we get the transition from less stable to more stable states. So this is a mathematical physicist way of conceptualizing all these millions of degrees of freedom of the body, of an animate system. Pretty amazing, but the amazing thing, even more so, for a student of scientist and a student of movement, is that these mathematical models work and they predict a lot. Predictions follow from the simple mathematics. But look, here's some data from my own experiments way back in the mid-90s. This is now where we're looking at right-handers and left-handers. On the bottom, we've got the frequency difference between the hands. So, get rid of those red lines. So you've got the right hand with a high frequency and the left hand with a lower frequency pendulum, or vice versa. We're comparing right-handers and left-handers and looking at the phase shift, how far they move away from perfect zero in phase or perfect out of phase, 180. This is like an error measurement, this is the difference in relative phase. All right, I'm out of time yet. So let's just look at the red lines for the right-handers. I want you to first notice that anti-phase shifts more than in phase. Okay, we're going to see that for the left-handers as well. But look at the red lines for right-hander data only. Also notice that there's greater shift when you put an external constraint of higher frequency in the dominant hand. So this shifts more than this. Sorry, this shifts in antiphase. This shifts more than this for the antiphase pattern when the person is wiggling the pendulums like this. Likewise for in phase. This shifts more away from perfect in phase than this. So these external constraints amplify the inherent asymmetry of the body. I didn't mention, but right-handers will slightly lead with the right hand, left-handers will slightly lead with the left hand. I should have emphasized that really hard and strong. There's an inherent asymmetry of the body. I'm going to show you these precise experiments that show what happens when you muck around with these inherent asymmetries. So with left-handers, the same story. Antiphase shifts the pattern away from perfect antiphase more than for in phase. So this out of phase pattern is not exactly 180 degrees, it's more like 190 degrees. I'm exaggerating it, but more like that. So there's a similar pattern right-handers, left-handers. And you can see, for example, for the right-handers, if you go to the situation where the lower frequency pendulum is the right hand, there's less shift than the opposite. That's the point. Now look at variability. The standard deviation of relative phase increases as the asymmetry increases. There's two values here of these manipulations, two data points. So the standard deviation goes up as the imposed asymmetry goes up. So we have a problem here. As you start messing around with the biodynamics of the body, you're going to see more variability and you're going to see more pattern shift in whatever pattern it is you're trying to get somebody to learn. Now look at this. Let's increase the rate, so-called control parameter. Let's go from 0.9 natural frequency of the pendulums to the natural frequency to 1.1 times the natural frequency of pendulums. Left-handers and right-handers both increase in their phase shift. So somebody, the biomechanical engineer earlier talked about increasing the rate. if you're going to increase the rate of some of these activities, you may well see an increase in the imperfection of the pattern you want. So here, this is an in-phase task. In-phase task? Yeah, I believe so. This was an in-phase task, and as you go faster and faster, the inherent asymmetry of the body gets magnified. This is predictable by the dynamical systems equation. Very simple equation. But it's beautiful, it makes these predictions. This is data corresponds with the mathematics. Now, you're going to get a shift in the pattern with increasing rate. There's a constraint for you. You're also going to be able to change it with attention. Look at this. Here is the relative phase. Plus meaning the left hand is leading, negative meaning the right hand is leading. For left-handers, right-handers, in-phase coordination. Now the subject is asked to put attention to the left hand or the right hand. Left-handers are telling the left hand will shift away from in-phase more than when attention is on the right hand. Likewise for right-handers. When they attend to the right hand, they put their cognition into the biomechanics, it shifts more. Attention, a cognitive factor, cognitive constraint, acts similar to a biomechanical constraint. But there's more. There's shift if there's attention, but look what happens to the variability. When attention is put into the left hand of left-handers, the variability, the standard deviation goes down. Right-handers attending to the right hand, they shift more, but the variability goes down. So when you ask somebody to attend to your limbs, or attend to some aspect of the pattern, attend to one of these tasks people are talking about, well, different things are going to happen for actually quite interesting and well-known reasons that have been looked at in these are very precise experiments in the motor control lab. So the variability goes down, but the pattern gets worse. The pattern is shifted further with attention, but the variability goes down, so you become really consistent at doing what you shouldn't be doing. So there's a problem there. So yeah, we just heard a wonderful talk on between-person coordination, and this is really where the game's at now in the last 10 years, following off from Richard Schmidt's work, collaborating with a lot of people. Under unintentional coordination, it's all over the place, with moments of synchrony and asynchrony. Well, with just looking at each other, with using visual information, not neurons, not muscles, not the musculature of the body, or all the sensory organs within the muscles, etc., visual information supports coordination. So the equations of coordination dynamics also now apply to between-person coordination. This is the beauty of the coordination dynamics perspective. It encompasses between-person coordination. So that was one-to-one coordination. Here's good old Muybridge from 200 years ago looking at two-to-one coordination. Right? You've got two on the left and one on the right in the blacksmiths. Here's an experiment I did back 1999. Two people moving levers that can either make a beeping noise, beep, 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 looking at different frequency of coordination, polyrhythm coordination patterns. The coupling, the informational coupling can be visual, haptic, using an elastic band, a rubber band. So when people are in phase, that feels like they're in phase. When they're out of phase, there's an increase in force and tension on the rubber band. So that's our haptic manipulation versus auditory. So there's a beep, beep, beep that they hear the other person. And we look at coordination between people using different information sources. And we find that the haptic is the strongest, not the visual, not the auditory. Haptic is strongest, then auditory, then visual, in terms of keeping them synchronized. So it really depends on the task whether vision and visual feedback will be better than, say, auditory. And now people are starting to tune into haptic. Okay. So, yeah, what we found in that research was there were transitions from one ratio to another. And this is a mathematical construction discovered by a guy called John Ferry in 1816. This is the real number line 0 to 1. Halfway is 0.5. Between 0.5 and 0 is a third. And where these numbers come from? 1 plus 1 equals 2. 3 plus 2 equals 5. And you can generate an infinite number of ratios. And the further down, the less stable they are. So number theory governs, amazingly, human coordination as well as electrical oscillators, various oscillating systems, will make transitions according to this pattern. The good old fairy tree story, which I cut my teeth on back long ago in 1993. I think Jeff Summers put that in the title of a paper famously. Okay, so this talk was affordances and coordination. And the haptic story goes back to this guy, James Gibson, 1966. Rediscovered the word haptics in his textbook, The Senses Considered as Perceptual Systems, not as sensory systems. The Senses Considered Perceptual Systems was James Gibson, a genius perceptual psychologist who gave us the concept of affordances. So I want to try and get you today to think about not just the coordination as a motor control task of oscillators, but the meaning of it, the semantics. This was Gibson's goal, to introduce the concept of affordances, the relevant things that are perceived in the world. So the affordance of the environment, or what it offers the animal, what it provides or furnishes, either for good or ill. I mean by something that refers to both the environment and the animal in a way that no existing term does. It implies complementarity of the animal and the environment. So I really wanted to go real quickly over what an affordance is using Warren's famous experiments on stair climbing. How do you know the maximum height of a stair? Okay, you've got the riser height. Okay, so the stair has got a riser height, and you've got a leg length, and you can do a ratio of the two of them. And it turns out that the maximum for most people, most able-bodied people, not old people, etc., not people with problems, physical or mental, for most people, the amazing thing is a ratio one can talk about 0.88. That's about 0.88 right there. So I'm pretty much at my limit. But notice I could see that, I could demonstrate that to you. That's the amazing thing, that you can see these things. So can you perceive the maximum stair height? Here's the data from Warren, 1984. First experiments on affordances. Hands up, how many people have studied this experiment on affordances? Okay, only 2 hands went up, so I'll do it. This is really important stuff. This was exciting. Short and tall people will say, yes, I can climb small riser heights in inches, or no, I can't climb large riser heights. So you get 2 profiles with a cutoff, psychophysical cutoff, which is like the threshold, 50% line. Short and tall people, right? But the amazing thing is, if you do body scaling, if you instead of throw away the physicist dimensions of height, and you turn it into a reciprocal relationship, an affordance concept of the body relative to the environment, riser height relative to the leg, the profiles line up. So somebody said everybody's different. Well, I take issue with that. As a scientist, you want to look for why people are similar. Right, Patricia? Yes, there are variables really important, intersubject variables, very important to study. A lot of insights from it. But also there seem to be some laws governing behavior. So that's the maximum height. What about the preferred height? Do you want to walk up steps like this? You know? No, because it's too high. So what's the preferred height? So Warren got an adjustable treadmill, stair mill from a hospital in the Bronx, brought it to the University of Connecticut, tested people biomechanically with energy measures, their calorie use, and you get 2 profiles for minimum energy use. So the so-called shorter group and the taller group at different heights of preferred minimum energy use, right? U-shaped functions for energy use. If you do the biomechanical scaling, you get the same profiles with a ratio of 0.26. That's the preferred height. About a quarter of your leg length is the preferred height that you could walk up all day. If you were going to Everest, you'd want quarter the size of your leg length steps. But can it be perceived? Perception and action. Perception. Can that be perceived? And Warren, same story, riser height. People chose, looking at slides, they looked at virtual slides of stairs. Short people chose this height. Tall people said that one is preferred. Do the biomechanical scaling, you get 0.25. Similar to 0.26. Same idea. Quarter of leg length. So people are so good at perceiving the world in categories. Affordances are related to categories. Categories of action. Not just how things look, but how they're related to action. So why are monument steps so difficult to walk on? Because they're too small. All right. So then, with my dear colleague here, Mira Peter, we started looking at not just bimanual coordination, but speech-hand coordination. Let's go from the spine up to the cortex, in this research program, getting more cognitive. So gestures are really important for communication, right? There's something to do with the body. So we looked at this little experiment, tap experiment, speech-hand coordination, where the task was to go faster and faster and faster doing this. Ba, 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 ba. Eventually there's a transition from anti-phase to in-phase, classic phase transition. So we looked at the data. Well, here's the data, you get the out of phase, you get the out of phase, relative phase around 180, as you go faster and faster. Then there's a transition to jaw and finger in phase. Briefly, some of the data, I'm just punchlining the data here. Right-handers versus left-handers. Difference is only on the right hand between pattern. Pattern affects the right hand, hand matters, handedness does not. So right-handers, left-handers both get that influence on the right hand, which is the left hemisphere, which is, language centers, Broca's area. Language is mostly left hemisphere for most people, even for left-handers, although they're a little bit dodgy, a little bit different, more interesting actually, left-handers. There's a pattern here that hand matters. Okay, so we're moving up to the cortex here, semantics, meaning, what's it all about? So this is Mir and my work on speech-hand. Then we asked, well then of course you have to ask, does this darn equation apply? And it does apply to the data. Don't have time to show you how it evolves. But this is the classic potential well equation. And as you increase frequency, it predicts the transitions beautifully. The summary of that was that the gestural time is left hemisphere. Attention needs to be increased. You need to increase the attention to maintain that anti-phase. And dynamical systems capture lawful evolution. And there's a rate-dependent semantics. The meaning seems to depend. We were intuiting then. The meaning depends on the rate in which you do things. So what's that doing for a coach looking at a student, or for a student, when rate matters so much? So this is the final experiment in this part, which is that we started looking then at the affordances of gestures. Can gestures influence perception? Imagine you're a coach. I want you to put yourself in the position of the student and the coach. Communication. What are you directing their attention to? Where do you see this and how tricky it gets? Alright, so we created an avatar and had people look at a big screen, virtual reality, and make like real life-size, make judgments of what this guy is saying. Now what do you think he's emphasizing? What do you think is the emphasis?
Put the book there now. Put the book there now. Put the book there now.
Who thinks put? Who thinks book? Book. Who thinks there? Everybody thinks there. Okay. What's going on? Those tricky experiments was we changed the gesture, right? You saw the guy gesturing maybe. Put the book there now, or put the book there now. The synchrony of the hand and the language is so important. If you put the gesture there, you get different amounts of agreement that book is being emphasized if the gesture is there. Or if the gesture is here, there is being picked. What you just saw was the gesture there, right? 50% say book, 50% say there. But, see that thing? That wasn't in all of the... That table is not... There's a no table condition. And so what we found was whenever we put the table there, people actually chose there more. So the context, the visual background, influences what people hear, what they perceive. It can get real confusing in communication. Imagine boardrooms and meetings. People don't know what the heck's going on just because somebody gestures in a different way. So it gets pretty bad, and this is how bad it gets. This is my final work that I'm doing these days. Actually, I'm trying to bring this to the real world of driver training. I'm working with kids tomorrow. I have to miss tomorrow, unfortunately. Got a driver day in Hamilton teaching kids to drive. And so back in the early 2000s, back in Griffith there, where Justin used to be, high student, old student, now professor, overtakes us all. So back here we were doing work on the driving centre, Holden sponsored driving centre wanted us to evaluate their stability-based driving program. They were teaching kids to drive by using their knees to brace by using the footrest. If you increase postural stability, then you relax the driver, then their attention frees up. That's the secret. Improved posture, increased stability. If you increase stability, stability-based dynamics, that's the secret, stability. So with all these fancy sensors, force plates and so on, GPS, well, focus just on the GPS. GPS data going around the track. Novices, unstable trajectories. Expert drivers, the trainers themselves, perfectly stable trajectories. So it's like a dynamical system's intuition here. This is kind of, hand waving a little bit, but it's the notion of experience versus instructor potential wells. Stability-based learning. We did an experiment on, here's Gibson, James Gibson, intuition about affordances, 1938. How does this car know? What's the optic flow, optical expansion? What's being used to know that that car needs to stop there because that car is going to go through? Anticipation, seeing the future. This is all about seeing the future. There's information now about the future. So we asked, can people perceive when to stop before a stop line? Here's a stop line between boxes, or a stationary vehicle. Couldn't use a stationary vehicle, used a line of boxes. So two conditions, people stopping before a stop line or stationary vehicle. And the significant difference was on the stationary vehicle, the car condition. So this is your affordances. I would put to untrained drivers are more cautious before the affordance of a car. Stop line doesn't matter. So the meaning of the world matters. And yeah, so we're trying to avoid this with motor control and motor learning. Police say the accident was caused by texting while driving. Wow, something should be done about those people. So we're all guilty of this, thinking that we're not the source of the problem. But there is a problem with distraction and lack of attention. This is what I want to emphasize finally, is the notion of attention. Now people talk about three types of distraction: visual, manual, and cognitive. And this is the big one with mobile phones, right? So you've probably all heard about the notion of inattentional blindness. You've seen the basketball video. Who's seen the basketball video? Right? So you're counting the basketballs. People haven't seen it, I'll show it to you later. Because you're trying to count the basketballs, you don't see something very important that happens. I won't tell you what. But when you're focusing so much on one thing, you become effectively, functionally blind to other things. This is a problem with mobile phones that I will be giving a talk tomorrow at a driver safety day about. But what we did way back when, early 2000s at Queensland, was look at the effect of a hands-free mobile phone. And you get a delay in the initiation of braking. Not reaction, forget about reaction time. It's bloody irrelevant. Anticipation, seeing the future. That's what skill is about, I put to you, not reacting. By the time you react to it, it's all over. All this, these beautiful sports that we were seeing earlier today, it's about anticipating. Reaction anticipation is what seems to be going on in your work, with beautiful experiments we're done at Kelso's lab on simple beeps. Reaction anticipation, which you're now making more ecologically valid. Where's the difference between reacting, turning into anticipation? So when you're approaching a corner, you've got to anticipate when to start braking. And that was delayed. Not reaction, but that's a delay. That's a delay in detecting the information, the optic flow information, the tau information, in fact, that we heard of. And that was a delay. That's one car length, so that means you're late in initiating braking. When you're too late going into a corner, you're too late coming out. So yeah, you can do all these experiments now with virtual reality. There are questions about that. This was the old lab at Griffith we had. That's Mira there doing some virtual exercise experiments in her more athletic days. Virtual experiments on virtual exercise. Can you get the same effect from running up a virtual hill as opposed to a real hill? There is evidence that yes, the lungs work in different ways. So what I've tried to remind you about today is the perception action cycle that we just heard about. But again, what it is I put to you is perception is not about meaningless things. Perception is about meaningful affordances, ultimately. If you can get your head around that concept, I think it will help. So perception is specific to the information. Information constrains action. So as I'm walking, I'm constraining my action with the perception. of the floor that a forward's walking on. The action reveals new information, so here I am approaching a table, which then constrains new perceptions of the affordance for the table, which allows me to step up or whatever, or bump into it. So this is the famous perception action cycle that you will have heard of. But importantly, I think this is worthy of greater attention. Your intention, what you intend to do, depends upon your attention, and vice versa. What you attend to depends upon your intention. Okay, there's always these circularities which one can talk forever about. But I think it is the crux of the problem is attention, and as coaches, all about the problem of how to direct attention, whether it's visual information or haptic information. But think about the affordances notion. See if you can get so-called ecological validity into the problem more so. I think it will make things more exciting and meaningful in your and our work. So thank you for your attention, and if we have any time for questions, otherwise I'll be around today. Cheers.
I think we definitely have time for one or two questions, because that was a very stimulating talk, and I would certainly like to hear a couple of questions before we go off for lunch. And the hat's still here, so... Yes, Rens, you can go first.
Thanks for the talk, that was really nice. I'm just wondering, with all the, obviously this relates to what I'm dealing with.
Absolutely.
The tasks that these dynamics are based on are, they be quite constrained in terms of it's only tapping or it's only moving your hand. I'm attempting to translate this to whole body movement.
Exactly.
How
Applaud you for it.
How do you think, is that worth it, or will it become so complex that these dynamics will be
No.
confused with all the other changes?
No, just don't forget these results. When you go faster, phase shifts happen. When you impose different kinds of constraints, there's a prediction about what's likely to happen given the body's asymmetry. I mean, asymmetry is everywhere. We're not symmetrical. And I think, asymmetry really is always worth thinking about which knee is the person focusing on. You've got very complex situations, mirror movements, looking at mirrors, and God, you put your head into spin what's really going on there. But I mean, we had it easy by just doing precise experiments with pendulums or what have you, and I've tried to make it more complex over the years in our work, trying to make it more cognitive and so on. But like, this is a very challenging task once speech comes into it. But absolutely, no, this is important to see where the boundaries on our knowledge are. This coordination dynamics theory is probably going to be overrun any decade soon, but it's still pretty powerful in many ways. But evolution of knowledge is what it is, and so it's important to see what the boundaries are and how far it can be pushed. But everything you said was valid, I think, the whole issue of what kinds of optical information are relevant. Yeah, this is all great work.
Can I make one addition to that question? Like, if you think about sports situation, it's not even just this coupling that the dynamics, the coordination dynamics, which arguably are always there. But then also when you're playing with someone, you might not like that guy that day because he says something mean to you.
Soccer, it's like Brazilian soccer.
How dominant do you think the coordination dynamics will still be if you look at the whole equation of the whole psychology of when you're interacting?
Well, I don't know what the future holds, but I do know that this is not the complete story.
Yeah.
I mean, I told you several stories there, but it might just seem that was coordination dynamics. I don't know how driving fits into coordination dynamics, but it is a hand attention problem, you see. This is why I moved into this area to look at. It's exciting from that perspective. It's not simple. We're complex systems. The cliche is we're a complex system. Yes, we are a messy, complicated, complex system. We need all these perspectives. Some are on the wane, such as motor programs. Some are on the increase, such as dynamical systems. We need them all, and it's interesting to hear all those perspectives. So, yeah, what you're hearing is great. The messier the problem. I mean, the Brazilian football example, so challenging but so real, and so easy to forget. Oh, let's not worry about that. It's too hard. Why not? Let's look at it. Let's brainstorm how to address that. But there are people working in social coordination. It's a big topic now. Schmidt and colleagues. Social coordination is the name of the game in coordination dynamics now, is how people are synchronizing or not. So, yeah, I'm proud to have been part of that history.
Fantastic. Okay, well, I think we should break for lunch now at this point. So can we thank all three presenters?